So for the rest of 12.1, we're going to talk about other surfaces. So on Tuesday, we talked about planes, which was really just a review. We've talked about them before this semester. To really figure out what these other surfaces are, we need to learn about something called a trace. And a trace is kind of like just a cross-section, a two-dimensional cross-section through a surface. And if we can identify what our cross-sections look like, we can use those as building blocks to put back together to figure out what the three-dimensional object looks like. So there's two surfaces in space that we know about right now. We know spheres. We talked about spheres back at the very beginning of the semester when we first introduced similarities between 2 dimensions and 3 dimensions. We didn't really do anything with them though. But I think we just very briefly looked at the formula. So that would be the equation for a sphere centered at x sub 0, y sub 0, z sub 0 with a radius of r. If you just cover up the z part, it's the equation of a circle in the plane. So all we had to do was tack on the z piece, and all of a sudden it's a three-dimensional sphere. And the other surface in space that we know is the plane, which is ax plus by plus cz equals d. That's our general form. And in this format, the one piece that we could pull out is the normal vector ABC. The D doesn't really have any significance right now. From the standard form, we could see a point that got used to help create it. But the D is a result of all those ABCs getting distributed and combined. So those are two surfaces that we've already seen at some point this semester, two surfaces in space. So the sphere, everything is squared and added together with the same coefficient. The plane, everything is linear and added together. So if we start playing with only squaring some of them or changing some of the additions to subtractions, it's going to change completely what these surfaces look like. Another thing that we said on Tuesday that's going to be helpful is when we started converting, when we were talking about polar coordinates, if we convert and a variable ends up missing from the equation, does anybody remember what that means?
Oh, yeah.
If the variable is missing from the equation, if I know something is in the xy plane, but there's no y in the equation, it means there's no restrictions on the y. Right. So if I'm told that I have a surface in space, that means it involves x's, y's, and z's. But if one of the variables is missing, that means there's no restrictions on that variable. That means that whatever the object is that's being represented in the two variables, it's going to be repeated forever in the direction of the variable that's missing. And these are called cylinders. What have we learned so far in our life about cylinders? What do you know about cylinders? Anything. Elementary school. Toilet paper. What's the shape of toilet paper?
Cylinder, two circles and a rectangle.
It's got circular cross sections. If you were to like slice it and unfold it, the surface area is like a rectangle. But it's got circular cross sections. It's like a circle that got repeated for a certain amount of distance in another direction. Technically, mathematically, a cylinder can be any shape repeated indefinitely in another direction. So when we first learn about cylinders, we usually talk about circles being repeated. The correct term for the cylinders that we learn in elementary school is a right circular cylinder. Right meaning they stand perfectly up and down. They make a right angle with whatever they're sitting on. Circular meaning their cross sections are circles. So the correct technical math term for the cylinders we learn in elementary school is a right circular cylinder, because there are lots of other types of cylinders. Any shape that gets repeated indefinitely along an axis is considered a cylinder. So this is when a two-dimensional graph gets repeated along the third axis to create a surface. Or I'm going to say along the axis of the third variable. And that third variable is missing from the equation. That third variable is missing from the equation. That's why this graph gets repeated forever in that direction, because there's no restrictions on that variable. So when you first see these equations, they're just going to look like two-dimensional equations. So we have to be told in the instructions that these are three-dimensional surfaces. Easton brought food. You brought Joa his own separate food? I thought you had something over there and you said, that's for you.
They actually got me a steak. They went to Restaurant Bargains.
So in these next few examples, we want to identify and sketch each surface. So even though you're only going to see two variables in the equation, these are surfaces. These are three-dimensional surfaces. Okay? Y equals x squared. So let's brainstorm a little bit. What do we know about this? Anything whatsoever. It's not a straight line. It's a parabola. So let's get a little bit more specific. It is continuous. Go ahead, Arturo. Okay. It has a minimum.
Facing the thought.
It's
Open.
so
Concave up.
facing up is kind of weird in 3 dimensions. So instead of say facing up, let's say opening in a specific direction. So what direction does it open? Opens in the positive y direction. It opens in the positive y direction. This is a 3-dimensional surface. That was told to us in the instructions. Which variable is missing? Z is missing. What that means is when I draw this parabola in the xy plane, that parabola is going to repeat forever along the z-axis. When we draw it, it's going to look like half a cylinder that's been squished, but technically a parabola goes for ever in the y direction, and then this thing's also going to go forever in the z direction. We can't draw forever when we draw, so we're going to have to stop it. The fact that there's a variable missing is what makes this a cylinder. And then the generating curve we said was called what? What 2-dimensional graph were we going to draw to help us make this? A parabola. So we're going to come up with some fancy term that puts those together. And it's called a parabolic cylinder. This thing is called a parabolic cylinder. It is a cylinder that is generated out of a parabola. So we've identified the surface. That was one of the things we were asked to do in the instructions, identify the surface. The other thing we were asked to do is sketch it.
So it would be like a ditch.
Yes.
Or the inside of a turbine tumbler or whatever.
The inside of a what?
You know the turbine tumbler where they have like the glasses that have like all
I hear turtle and I hear turd.
Turbis tumbler.
Turbis tumbler.
Yeah.
Turtle.
Turbis tumbler, whatever.
Turtle?
What?
Okay, I gotcha.
Purpose tone.
Yeah.
How they have
Mhm.
a kernel inside.
But it's not cup like that.
Right, it's obviously.
So
the
it goes
top
forever. Right. It would have to go forever in one direction. So let's try to draw this thing. So we've got our X, Y, and Z axes. And remember, these are different than how we would draw just the XY axis. So you need to be careful with how you draw your parabola. That's why I wanted us to write down what direction the parabola opened in, because that's important. So we've got a parabola in the XY plane that opens in the positive Y direction. So the XY plane is flat, the flat plane. And the parabola opens in the Y direction. Mm-hmm. And since Z is missing from the equation, technically Z is not restricted. So there's nothing in that equation that's telling me where on the Z-axis to draw that parabola. So I can draw it anywhere on the Z-axis. So I could also draw it up here. I could also draw it down here. So what ends up happening, I'm going to try to clean this up a little bit. I'm going to make the back ones come out a little bit farther. I have been able to draw this pretty decently in the past. We shall see. And now that I have colors, it should be even better. Is this making it worse? So the blue is kind of the outside coming out at us, and the red is the inside that goes towards the back. And if we slice this thing horizontal, we're seeing parabolas. The shape is a parabola. And there's just an infinite number of them just stacked on top of each other over and over and over again, getting repeated up the Z-axis. Because Z is missing, that means Z has no restrictions, and we can draw it at any Z value we want to. So it's like taking a piece of paper and doing that. No. Because all we have is a parabola generating it, and parabola is just a curve. It's not a closed figure. Parabola is not a closed figure. What should I say? Figure?
Figure.
Do you say coupon or coupon?
Cupid.
It's coupon.
Oh, it's a Cuban. It's not figure.
Do you say soup or soup?
Soup.
So coupon.
What?
It's spelled exactly the same.
It's got different letters.
No, it doesn't.
My friend was, we were arguing with my friend, he was like, why is, is it syrup or syrup?
So we can't draw it forever, but technically it goes forever. It also goes forever up and down. So these cylinders will always have some two-dimensional kind of graph that helps to generate it, and then it will get repeated forever along the axis of the missing variable. Did I call that A? I did. You could also call this thing a cylindrical paraboloid. Cylindrical paraboloid.
Is it before or after? Doesn't it state your here? Are you north of the border or south of the border?
Y squared over 9 plus z squared over 4 equals 1. What do we know about this thing? Anything whatsoever? They both have to be 1/2. A half plus a half equals 1.
So something squared has to be half.
That would be true. That would only give us 1 point on the graph, though.
Let's see.
To build an entire three-dimensional surface, that would take a very long time.
Solve equal for solve for y and solve for z.
Because they have squares on them, if we solve for y and solve for z, we'd end up with plus or minus square roots in both cases. So that would be kind of ugly as well. Do we know what the shape is? Almost. They've got different denominators, which means it's an ellipse. They don't have the same coefficient, which means I'm moving a different number of units in the y direction than I am in the z direction. So it's an ellipse. So Tyler, how did you know that?
Just from having it in previous lessons. Doesn't the hyperbola look similar?
It does. There's one tiny difference in the hyperbola equation. Does anybody know? Has anybody learned about hyperbolas before?
Yeah.
Is that a minus?
It's got a minus. In English, it's hyperbole. In math, it's hyperbola. And isn't hyperbole is when like you massively over-exaggerate something?
Yes.
Yeah. I don't know how I know that. I have a photographic memory. So this thing is an ellipse. What plane are we going to draw this ellipse in? It's going to include the z, but a plane has two axes. The YZ plane, yes. It's an ellipse in the YZ plane. I know you're trying, Eason. Which variable is missing? Since we were told it's a surface. X is missing.
First.
Which means once we get our two-dimensional ellipse drawn, we are going to repeat it forever in the x direction. Okay? Let's try to name it first. You're almost there. Elliptical cylinder. Yep.
Yeah, that's what I was curious. That's what I was thinking.
And it's because of the shape those little petals make when they go.
I hate that. It's like a natural motion when you're in the walk, try to walk on this.
Elliptical cylinder.
Or something else. Something like-
No, this is fine. Doesn't have to be another one. Cylindrical ellipsoid. Mhm. So we've got an ellipse in the YZ plane. The YZ plane is facing us. It's like the board. So those numbers underneath the variables are the squares of our radii. So in the Y direction we go 3, in the Z direction we go 2. That's ugly. I don't like that. It was a potato.
Say it again.
I don't like that one either. All right, I'm not drawing it again. That two-dimensional ellipse is going to get repeated forever along the x-axis. Right now, I've just got it at x equals 0 on the YZ plane. I could draw it at x equals 1. I could draw it at x equals 5. I could draw it at x equals -3.
Which one's the x-axis? Which one's?
The x-axis is coming at us.
Oh.
In this class, the x-axis comes at us. I know in physics it's different.
So why?
Why do we do that?
Why is it not like? So technically, it's facing like.
It's facing us.
This.
Uh-huh.
Okay.
It's facing us. So if I draw this out at like x equals 3, it's going to slide out at us at an angle because I've got my x-axis angled.
Close enough, right?
Ooh.
That's close enough. There's a reason why computers do all the drawing, you know.
Does anybody know anything that's this shape?
A hot dog.
Slide.
A hot dog is like a perfect circle. A slide?
If you're looking like at a lighter.
A lighter, yeah.
And,
A lighter.
oh, a cigarette lighter.
Oh, yeah.
Cigarette lighter? Um, you know how Lay's has made a new type of chips to copy the Pringles? The Lay's cans are like this. The Pringles cans are perfect circles, but the Lay's cans, they've made
I would
kind
say
of flat,
egg.
elongated.
I would say an egg, so.
Hmm?
An egg, like, you know.
But an egg is not.
Yeah, but it's not that way.
Mhm. So it's like a pipe, but it's not a circle cross section. It's an ellipse cross section. Question so far? So this is one group of surfaces in space. They're cylinders. And when we see their equations, they're a little bit misleading because they only have two variables. But we have to be told that there are surfaces so that we know it's not a two-dimensional graph, it's a three-dimensional graph, so that we know to take that two-dimensional graph and repeat it forever along the third axis and make a surface out of it. We will in the next chapter. We've got to learn derivatives first, and then we'll do antiderivatives. So this chapter, we're going to talk about derivatives and what all the derivatives mean on this graph. And then we're going to do antiderivatives and get volumes and stuff. So the first group was cylinders. And what makes them unique is that there's a variable missing. Our next group are called quadric surfaces. And what makes them unique is they have squares. They always have squares. I always think that too. I always think of quad as meaning 4. And then I've read some sort of article. It bugged me so bad because you always think of quad as meaning 4. But then you think back to algebra class and quadratic equations. Quadratic equations are squares, square equations. And I guess there was something back in Europe, in universities in Europe, they called the common meeting area the quad because it had two distinct sides to it. It has something to do with that. I finally got fed up with it. I kept wondering why they kept using quad as a prefix on things with 2, when usually in America we use quad as meaning 4. It bothers me. It bothers me and it's confusing. But in this case, it's meaning 2. In this case, it's meaning 2. There is one equation here where one variable is not squared. All of their equations, all of their variables, everything's going to be squared. So that's why I said mostly. Everything's squared here in our quadric surfaces. And I'm going to go through, I'm going to show you just the first one, then we'll have a break. Okay. The first one's really easy. And it's called an ellipsoid. An ellipsoid. And as we go through this, I'm also going to talk to you about traces. Because being able to look at this equation and tell that it's an ellipsoid requires you to be able to identify the traces. So we need to talk about what exactly a trace is and how we find a trace. So the formula for an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Looks very similar to the ellipse we just did in the last problem, except it's got all 3 of them in there. So what we're going to do to help us identify these solids is we're going to use traces to identify the 2-dimensional cross sections, and then we're going to piece them back together to create the solid. The easiest way to do a trace is to just let one of your variables equal 0. There are some cases where you can't do that, and we will come across that today, and I'll show you why and what we would do in those cases. But the easiest way to do it is just let one of your variables equal 0. If I want to know what the cross section for this surface looks like in the xy plane, then just let z equal 0. In the xy plane, z equals 0. So in general, a trace is a cross section of a 3-dimensional surface and it's found by letting one of the variables just be equal to a constant.
So it doesn't have to be B.
Huh?
It doesn't have to be B.
No, we're going to do it for all 3. Because our surface has 3 different cross sections. If you think of a box, it's got a length, a height, and a width that could all 3 be different, technically. So all our surfaces are going to have 3 different cross sections. The easiest constant to let them be equal to is just 0. But there are a few cases where we can't let it be equal to 0. And we'll come across those and see what to do when that happens. So for our ellipsoid, I'm going to write the equation again. We want to know what the traces are. I want to know what the individual pieces are that come together to make up this surface. So for my XY trace, I'm going to let z equal 0. And most of the time when we let a variable equal 0, it just wipes that out of the equation. So if I let z equal 0, we're left with a two-variable equation. We're just left with a two-dimensional curve. We're left with x squared over a squared plus y squared over b squared equals 1. And what is that? If we were to graph that, what would it create? Almost an ellipse. If a and b were not the same, it would create an ellipse. So when we slice this thing and we look and see what it looks like in the xy plane, it looks like an ellipse. All right? If we look at the YZ trace, and we do that by letting x equal 0. That's just going to wipe the x out of the equation. And that's going to leave us with y squared over b squared plus z squared over c squared equals 1. And it's another ellipse. And then there's one more trace we can check, xz trace. And what do we do to find our xz trace? We're going to set y equal to 0. And what sort of curve will that create? An ellipse. So no matter how we slice this thing, we're always getting ellipses. And I really suck at drawing this, but I always try anyway. And actually, I did find that leaving off the axes helps. So let me try that. So the XY plane is the flat horizontal plane that's parallel to the floor. That is an ellipse. So pretend that's flat. And we're looking down on that. Okay? I'm going to label these and do them in different colors. The YZ trace, it stands vertical and we're facing it like it's the board. That is also an ellipse. The XZ trace also stands vertical, but it's turned 90 degrees from the YZ trace. So this one looks more like a sphere, but depending on the ABC values, any of these points can be stretched out to make this shorter and fatter or taller and skinnier. More like an egg shape or a football shape or something like that. But no matter which direction we slice this thing in, we're getting an ellipse every time. So knowing those basic two-dimensional objects can be very helpful in deciding on what the three-dimensional surface is going to be. And when all of your traces are ellipse, they come together to make an ellipsoid. Very similar to a sphere. With a sphere, we're going the same exact distance from the center in all directions. There's one radius that works in every direction. With an ellipse, it's not perfectly equal in every direction. We've got those different radii out in those different directions. Questions so far? Engineering, manufacturing, 3D printing. Pharmaceuticals. You want to make pills? Almost all pills are this shape. Many, many pills are this shape. You want to make some drugs, Eason?
You can talk with Jamie though.
I'm going to pause the video. I want you guys to try this one. I want you to try to figure out the traces and what it's going to look like. Yes.
We can't just pick a random one.
What do you mean pick a random one?
After the trace, we can't just set one randomly equal to zero.
You're going to have to do all three. We need to know what it looks like in all three dimensions. We need all three of them. We need the XY trace, the YZ trace, and the XZ trace. Would you rather do it alone on your paper? Or do you want me to
Oh, are you gonna
ask for info? I'll give you a minute to jot some ideas down. So this is the only one, I believe. No, there's two. Where we've got something that's not squared. And I've got it up where the z is not squared here, but we could easily turn this around and say x equals z squared over c squared plus y squared over b squared, or y equals x squared over a squared plus z squared over c squared. And that's just going to change the orientation of the graph. So it opens in a certain direction. It's easier for me to draw that way. And typically, in 3 dimensions, if we can, we like z to be the output variable. So if we can solve for z, then it's considered a function. Did anybody get stuck right off the bat?
I was going to set these one equal to 0.
Yes, if you set z equal to 0, you might have a problem.
Radius is 0.
Yeah. That's one of the cases where you might want to think of z equal to a constant. So the only time a sum of squares is equal to 0 is at the point 0, 0. So you could set z equal to a constant as well, and you could do any constant you want to. What do we usually see x squared over a squared plus y squared over b squared equal to? And equal to 1, and it's an ellipse, right? So if it's more convenient and it's more helpful, and it's more easily recognizable, you can set it equal to some other constant. And this is one of those cases where equaling 0 doesn't really make a whole lot of sense, but equaling 1, and voila, we've got an ellipse. Okay? So our xy trace is an ellipse. And I don't get that by plugging in z equals 0. I get that by plugging in z equals 1. Because the rule for a trace is not plug in 0, it's plug in a constant. It's a cross section. Z equals 0 is just a really convenient one usually, but it's not the rule. Now for our other two traces, I would use 0. If we let x equals 0 to find the yz trace, what two-dimensional equation are we left with? No, we're going to let y squared over b squared. The b is just a number, so don't let that mess you up. If I have a single linear variable is equal to a squared variable, think back to what we would do in algebra class with that kind of equation. What would that graph look like? If it was just y's and x's, what would it look like? It would be a parabola. If one was linear and the other was quadratic, it would be a parabola. So this is a parabola. We need to know what direction it opens in. So again, think back to algebra class. Y equals x squared opens in what direction? It opens in the positive y direction. So parabolas open in the direction of their linear variable. So in z equals y squared over b squared, it's going to open in the positive z direction. The b squared is just a number. It's just going to adjust how widely or narrowly the parabola opens when it opens. All right, xz trace, if we let y equal 0, we've got z equals x squared over a squared.
Does that mean y of x is like y squared over b squared equals x squared over a squared?
They could be, but they don't have to be. They could be. There are other values, like on the unit circle, if A and B are equal, there are values on the unit circle that satisfy this equation that are not equal, like radical 3/2 and 1/2 square and add together to make 1. So z equals x squared over a squared. One of them is linear, one of them is quadratic. What's the shape? Parabola. What direction is going to open it in? Positive z. So we've got another parabola opening in positive z. I know what the cross sections of this surface look like in all 3 directions. And we're going to try to put them all back together to create a surface. I haven't told you what the name of this is yet because that would give away what the traces are. Usually those cross sections, whatever those 2-dimensional cross sections are, help us to name the object. So if I told you what the name of it was, you would have known what the cross sections were. I'm going to draw my parabolas first. So my YZ trace, that is what we're facing on the board. We've got a parabola opening in the positive Z direction. The XZ trace is also a vertically oriented plane, like the YZ plane, except it's turned 90 degrees. And in that plane, which cuts into the board, we have another parabola opening in the positive Z direction. So that one's like starting out at us and cutting into the board. Now remember, we said when Z is 0, it's just a single point, 0, 0. But as we slice this thing at larger values of Z, constants of Z, we see ellipses. So the XY trace is an ellipse. So as we slice this thing horizontal, we see an ellipse.
So it's just a watermelon. A little bit of deformed watermelon. Watermelon.
Except ours goes up forever.
Yeah,
Yes.
really big watermelon.
Yes, the bottom of it looks like
The ideal,
a watermelon.
it's like a net. Or like an upside down bird cage.
Yeah. Upside down bird cage.
Sure.
And your watermelons are square, so they're easier.
I've seen that. That's weird.
I think it's in Japan.
Easier to cut and store and package and ship. So we saw 2 different types of traces. What were they? Ellipse and parabola. We need to come up with a crazy name that puts them together. A cone is going to be pointy.
Parallel cylinder.
It's not a cylinder because we didn't have one shape get repeated forever.
Elliptical paraboloid.
Yes, elliptic paraboloid. Very close. This is an elliptic paraboloid. The names are just based on the traces that are used to create them.
Could also be called quadratic ellipsoid.
No. Quadratic just means there's squares in the problem. The ellipsoid means it's made out of ellipses. So that doesn't take into account the parabolas. There are several more that we need to talk about. Ready? Questions? Anybody have questions about the traces? Most of the time you can just do 0. If for some reason 0 is not making sense or you're not recognizing what sort of graph it makes with 0, you might have to use a different number. Usually 1, because a lot of these other equations, they have 1 equal to 1 in the conic sections. All right, we're gonna go. We're gonna start going a little bit quicker. All right, I'm gonna give you the names though this time, because these next two their names are really weird. And you're gonna wonder why in the world they named them this, but once we see the picture, you'll see why. In this one, we actually have something this shape close by here. This next one is called a hyperboloid of one sheet. A hyperboloid of one sheet. Hyperboloid means it's made of hyperbolas. A hyperbola, it's kind of like a parabola, except there's 2 of them and they face away from each other. Yeah, they don't touch. The equation for a hyperbola looks exactly like an ellipse, but the plus is replaced with a minus. So you can recognize the equation for a hyperbola. Look for an ellipse, but with subtraction. So we'll see it in this one. All right, for a hyperboloid of one sheet, the equation, or one possibility for the equation, if we move around where this subtraction is, it will just change the orientation of the graph, which direction it's opening in. So we'll get a little review of hyperbolas as we do this. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. XY trace, let z equal 0. We've got an ellipse. YZ trace, you're going to let x equal 0. It's a hyperbola. It's a hyperbola. And ellipses don't have direction. It's the format for an ellipse, but the addition got changed to subtraction. It's a hyperbola. And one thing that we have to add to our description is what direction it opens. That's also extremely important. Hyperbolas open in the direction of the positive variable. What did you say?
He said, "Don't make out the direction right." He said, "Oh no."
Negative x. There's no x's in the equation. Just sit and observe for the rest of the day. Just let it soak in.
It's okay, Ethan. It's going to be okay.
All right, so this is a hyperbola. They're squared and subtracted. That's what makes it a hyperbola. The one that is positive in front is the direction that these hyperbolas open in. Okay? So these hyperbolas are going to open in the positive and negative y direction. Hyperbolas always come in pairs. There's two of them, and they open away from each other. So they open in the positive and negative y direction. Because the y is the positive variable in this equation. The z has the negative in front of it. They always open in the direction of the positive variable. Easton, I want you to redeem yourself.
Hyperbola. What's the negative extra?
Beautiful. Absolutely brilliant. The xz trace is x squared over a squared minus z squared over c squared equals 1, which is again a hyperbola. The positive variable is the x. That means it opens in the positive and negative x direction.
So the shape is like two fingers back to each other.
Were you
I
serious?
was waiting till you draw it.
Okay. You were serious, weren't you?
I mean, yeah. For my drawing, if I'm drawing it right.
Wait just a second. I'm going to say no.
Okay.
Okay, hold on just a second. I'm going to do the ellipses last because the ellipses are what's going to connect all of our hyperbolas together. I'm sorry. Sometimes I don't know if you guys are being serious or not. So we've got a set of hyperbolas in the YZ plane. The YZ plane is the board that open in the positive, negative y direction. So they kind of just look like parabolas
Okay.
facing away from each other. Does that change the whole thing?
Yeah.
Okay. I'm actually going to pull them in closer to each other. We don't really know where they are right now because we don't know any other values.
So it doesn't touch that.
It doesn't. There is also a set of hyperbolas in the XZ plane opening in the positive and negative x direction. So that's like forwards and backwards. So back here and up here. Yeah, sorry.
Tree trunk.
Tree trunk.
Tree trunk.
A tree trunk is a very good guess. Now, there are ellipses in the XY plane that connect all of these.
Figure out how to do this. Saving is always close by. I'm trying to figure out.
Well, if you guys are native Rocky Mountains and if you haven't traveled very far, you might not know.
Yes, it is. It's a black hole.
Anybody play disc golf?
Thank you.
How many different courses have you played?
1, 2, 3.
It's near a disc golf course
Oh, were you looking?
in Apex.
Whoa. You said it was in a big
Think- Yeah. Sharon Harris. Yeah.
Did you already say that?
No, I was waiting for one of you guys to say it.
Oh, yes, I think we're actually. We're next to a spider farm.
When I attempt to draw it on the XYZ, it goes terribly wrong for some reason.
You should get one of those like 3D pens. I'm sure
Somebody
that-
in my Calc
that
3
was-
class in the fall, was it in the fall or last spring, had one, and he brought it to class, and we couldn't do anything with it.
They're pretty hard to use.
Yeah, it was really hard to use.
Did this thing.
No. No, but it dried, it cooled down and dried so fast we can never get anything to stick to each other. Yes.
Oh my God, this is gonna be terrible.
One of them. You only have to do one. I'm not judging you on your artistic abilities.
Better not.
You just do like random like scribbles. on
Eason.
Xbox Link.
Exactly. Look at mine.
Yeah, but you see mine much worse.
So it might be better to draw it off of the XY plane and then insert, or XYZ and then insert the XYZ later. I have found that I draw it much nicer.
That's all like, can I draw each plane individually?
No.
When I put it together,
It's exactly what it is.
I can't draw
So,
two.
nuclear reactors are not ellipses, but it's,
You can draw that one left, so it's on the left side.
That's still not great, but it's way better than the one above it.
That one's kinda like a liquid.
Huh? It looks different. All right. This is a hyperboloid of one sheet because when we put this all together, it made one solid object. The next one is called a hyperboloid of two sheets. Mm-hmm. What am I doing? This is the last one we're gonna have time for.
is there any reason why?
It's used in front.
It could be written with them in any order. I could have the X in the front, I can have the Y in the front. It would just change the direction that the stuff is pointing in. I could have X minus Y minus Z, I could have Y minus Z minus X. The traces would not change, but it would change the direction that things are pointing in. It would still be a hyperboloid of two sheets. The traces would still be the same, but we would just say like opening in a different direction.
See, no one would come up, before Carolyn comes up, they want a model of everything.
The XY trace here is tricky.
It's just impossible.
If we let Z equal 0, I've got negative x squared minus y squared equals positive 1. Mathematically, that doesn't even make sense. But if we let Z equal a constant,
Make it equal to and subtract the other side.
exactly, we would make it equal to 2, we would subtract it over, and then it would be negative 1, and then we would multiply everything by a negative 1. So I would make sure actually that Z squared over C squared equals 2. I would make Z squared over C squared equals 2. And then I would do some manipulating of this equation and have x squared over a squared plus y squared over b squared equals 1. So the z equals 0 here is not even possible, because you have a negative equal a positive, which is not going to happen. Which means this graph has no points on the z-axis. It doesn't have points until you move away from the z-axis, or which would be up and down, I guess. Once you start moving away from the z-axis, then it starts having values. And what shapes does it start to create as we move away from the z-axis? As we move up and down the z-axis?
Wait, did you just ask a question?
I did. What's the xy trace? All right, gotta do this quick. What's the xy trace? X squared over a squared plus y squared over b squared equals 1.
Circle.
It's an ellipse.
Oh, b squared, my bad.
Just because we've got different, A and B might be different. So it's an ellipse. All right, YZ trace. Fast, fast, fast. We've got z squared over c squared minus y squared over b squared equals 1. That is a hyperbola because it's a difference of squares. What direction does it open in? It opens in the direction of the positive variable. We're going to have parabolas opening, hyperbolas opening in positive and negative z direction. XZ trace is z squared over c squared minus x squared over a squared. Is another set of hyperbolas. Again, opening in the positive and negative z direction. This looks exactly like the last one. There's one tiny difference. What's the difference in this? Say it more specific, Adam. There's one difference in the traces. If you have notes on the last one. In the last one, our hyperbolas opened in different directions. One set of hyperbolas opened in the y direction, the other set of hyperbolas opened in the x direction. Okay? Yep. In this one, both set of hyperbolas open in the same direction.
Yes. Like that.
We're going to have two bowls. Yep. So in the YZ plane, which is the plane that we're looking at flat on the board, we've got a set of hyperbolas opening in the z direction, the positive and negative z direction. In the XZ plane, which slices perpendicularly into the board, we also have a set of hyperbolas opening in the positive z direction. And now these two bowls still are not connected, but the arms of these bowls are connected with ellipses. So we see this is called a hyperbola of two sheets because our traces are again ellipses and hyperbolas, but because those hyperbolas, both of those set of hyperbolas are opening in the z direction, they don't end up connecting, and we end up with two completely separate surfaces. So it's a hyperbola in a hyperboloid in two sheets. And again, we can change around in this equation which variable comes in the front and which one come behind the minuses, and that's just going to change the orientation of this graph. So we've got z as the positive variable, and this graph opens in the z direction. Our bowls are pointing up in the positive z and down in the negative z. So if we put x in the front, they would open in the positive and negative x direction. If we put y in the front, they would open in the positive and negative y direction.